All right, my calculus friends. Mr. G Math coming at you live, all alone. Just me, doing the prep, 6-1. I am hoping you're watching this and that you take time to try to learn this. Please don't give up. We will learn and be better at calculus if we make that choice. I'm here to support you. We're going to get through this. 6-1 is a continuation of the fundamental theorem of calculus. Remember that the derivative and the integration, they undo each other, inverse operations. So you can see that what you're integrating, and if you take the derivative, they undo each other and you're left just with 2x subtract 3. The following examples serve as an informal guide to discover the second fundamental theorem of calculus. How do I integrate that? Well, I'm going to add 1 to the exponent and then divide by that exponent. I'm going to add 1 to the exponent, divide, but I don't need to divide by 1. And I'm going to substitute in. The upper bound in this case is x, and the lower bound is 0. If I plug in x, notice the 2's divide out. I'm going to be left with x squared minus 3x. What happens when I plug in 0 is that you would ultimately subtract. The answer is going to be 0. And subtracting 0 doesn't do anything to that. So your answer is just x squared minus 3x. So let's continue that thought over here. What would happen if you integrate, which we just did, and then take the derivative of what you integrated? Well, the beginning part we just did. That's here. That's the integration. What's the derivative of what we just integrated? Well, the answer is 2x minus 3, right? From here, what we did before. So we did the first part already, the inside part, and then you take the derivative of what you did. See, they just undid each other. Nice, simple rule. So it says, do you notice anything yet? And again, did you notice that integration and derivatives undo each other? So now let's try here. So this is more of a general case. How do you integrate for that function? So you integrate the derivative. So that means that we just plug in the upper bound minus the lower bound. So what's the integration to f prime? It's just f. And then you plug in x first, subtract, plug in 10. Here, what happens, again, with the first part we did, right? This first part, what was the answer? F at x minus f at 10. What's the derivative of what we just did? Well, the derivative of f at x is f prime at x. The derivative of f at 10 is some constant, and the derivative of any constant is just 0. So the answer is just f prime at x. Can you see in one direction and the other that these two things undo each other? Okay, so it says for any constant a, so that's an important part, that it goes from any constant to a variable. They then undo each other, and you just plug in what that variable is. If f is continuous, from a to x. So a is a constant, x is a variable, and that basic rule that derivatives and integration undo each other is something we can use, a basic property. Okay, so that's the beginning understanding. What is it again? Derivatives and integration undo each other. Okay, now there's some layers to this rule. Let's look at 5 and see some layers. So now find this. So if I find this, if I integrate f prime at t, it's f at x, or f at t, and then I plug in the upper bound and then the lower bound. So if I plug in the upper bound, it's f at x squared, minus, plug in the lower bound, which is f at 0. Let's do it again. Number 6. We just did this beginning part. We said it was f x squared minus f at 0. How do I take the derivative of this? Well, the derivative would be f prime at x squared, but we got to be careful. Do you notice that inside the function we have a hook? See, before, inside the function was just x, and the derivative of x is 1. But it's x squared inside the function. What's the derivative of x squared? Is 2x. When I take the derivative, this is the chain rule. The derivative of the outside times the derivative of the inside. And then the derivative of f at 0 is just 0. But notice the layer on there in terms of that 2x is something we had to include. If you look at the bound, it creates a chain. That's what we're discovering. Okay, let's do it again. Number 7, integrate. F prime at t is just f at t, and you plug in the upper bound, subtract, plug in the lower bound. Now when you take the derivative, you got to remember the hook. So it's this part here, we already did. That's here. So that part is right there. Take the derivative of what you just did. It's f prime at 2 at x, and then the hook, minus f prime at x cubed, and remember the hook at the end of it. So when we look at our bounds, if it's not just a constant to a variable, if it's more involved, see how these bounds are more involved? Those bounds create hooks when we take the derivative. So what changes did you notice? So hopefully you notice the bounds create those hooks. So the second fundamental theorem, including the chain rule version, is I want you to notice that they still undo each other, but you have to remember that the bounds can create hooks that you have to include. So look at the bounds and take the derivative of the bounds and hook it on. If the derivative is 1, you don't have to worry about it. And if the derivative is 0, you don't have to worry about it. So if I look at number 9, look at the bounds. X to 0. So be careful. Order matters. So when I integrate and so on, what would I plug in first when I integrate? Well, first you plug in 0. And the derivative of 0 is 0. So first it's 0. Then, when they undo each other, what number are you going to plug in? Or what letter? Is x. And notice the order. Notice the variables at the bottom and the constants at top. That then makes the answer negative. And that negative belongs to both. So it's negative 2x plus 3. That order matters. So notice that when you integrate and you plug in 0, that's going to be a constant, whatever the number is. When you take the derivative of a constant, the answer is 0. That could have said x to any number, not just 0, and would have had the same answer. If it was 10, well, whatever that constant is, the derivative of that would still be 0. And then you subtract the fundamental theorem of calculus, then plug in the bottom bound, which is x. What's the derivative of x? It's 1. Do I need to put the 1 as a hook? Because times 1 didn't change anything. And then that subtract sign gets distributed. Okay, let's try it again. Number 10. Notice the bounds from 2 to 5. No variables. Well, what happens when I integrate this and then take the derivative? Well, when you integrate, you're going to plug in 5 first and get an answer. Well, the derivative of whatever number you have is 0. Then, again, when you integrate, you're going to plug in 2. So subtract, and whatever answer that is when you plug in 2, again, is a constant. And when the derivative of a constant is 0, so that answer is 0. So if we have a constant to another constant, this rule of derivatives and integration just gives us the answer 0, because taking the derivative of any constant gives us the answer 0. 11. Look at the bounds. Do you see negative 1 and x cubed? Order matters. We start with what? X cubed. So they undo each other. So instead of t, I'm going to put in x cubed squared plus 2x cubed. And then is there a hook on top of that? So what's the derivative of x cubed? 3x squared. What will happen when I subtract and I plug in negative 1? Well, when you plug in negative 1, it's going to create a constant, whatever that answer is. And the derivative of a constant is 0. So I don't need to put subtract 0, but that's the answer right there. 12. Again, look at the bounds. Do you see the hooks there? They're variables. And when you take the derivative, you can see that you're going to have hooks involved. So first, the upper bound. So what am I going to plug in first? 3x. So where there's a t, plug in 3x. And then the derivative of 3x is 3. That's the hook. Subtract. Now we're going to plug in 2x. And again, there's a hook. So you plugged in 2x for t, And what's the hook? What's the derivative of 2x? 2. Look at the bounds. F at x and g at x, really generic. So when you integrate this and take the derivative, the first thing you do is plug in the upper bound. So where there's a t, I'm going to plug in g at x. And then the hook is the derivative of whatever g at x is. Subtract. Now I'm going to plug in f at x. And then the hook, whatever the derivative of f at x is. All right, 14. Again, look at that. See that lower bound is 0? So when I plug in 0 and take the derivative, that's what's going to happen. But look at terms of take. It says take the derivative of that. So that's what f at x is. And if you take the derivative of that, they undo each other. But look at the bounds. So the first bound, the upper bound, is 3x squared. So where there's a t, I'm going to plug in 3x squared. Now all of that is to the exponent 10. And then there's a hook. What's the derivative of 3x squared? It's 6x. Then when you plug in 0, you get a constant, and the derivative of any constant is 0. So you don't need to put subtract 0 down. Anyways, this is the next level of the fundamental theorem of calculus. Turn the page. Interpretation of rate graphs. Graphs of rates are common in calculus. Duh, right? Because derivative means rate, slope. While the horizontal axes in such graphs may stand for many things, it often stands for time. The vertical axis stands for some indicated type of rate with respect to time. In rate graphs, a point on the graph represents a value of the indicated rate at a certain time. So there, it would be something per something. A slope represents a rate of change at that indicated time. Something per something per something. And the signed area between the graph and the horizontal time axis represents a definite integral, which has undone the indicated rate to produce an accumulated value. In this context, an integral may be thought of as an accumulator. One of the definitions of understanding an integration is understanding that it has a long S that adds up and accumulates all the stuff. Okay, the graph at the right models the rate of rainfall in inches per hour from midnight until 6 a.m. during a tropical rainstorm. So, one axis has time, the other is a rate, rainfall in inches per hour. Write a complete sentence to explain what point A on the graph represents. Include numbers and units in your answer to this example and examples that follow it. So numbers and units. Here's point A. So first of all, the numbers. 3 and what's the other number? 1. So what does 3 represent? So it means at t equals 3 hours. Well, do we have any other information about it? It rained from midnight to 6 a.m. So 3 would be what? If 0 is midnight, 3 would be what time in the morning? 3 a.m. So at what time? At 3 a.m. What's happening? It is raining. And it's raining at a rate. So it's raining at what rate? At a rate of, and that's where the second number comes in, 1 inch per hour. Done. The time and the unit, and it's simple, but we have to include all the important parts. It's not the paragraph that matters, that you include all the math information that you need. What is the slope of the graph between points A and B? So between A and B, the slope is a flat line, horizontal line, which the slope would be 0. Write a complete sentence explaining the meaning of your answer to example 16. So again, we're going to start with time and then understand the rate. So what time is happening from A to B? So A we said was 3 a.m., B is 4 a.m. So between 3 a.m. and 4 a.m., what is happening? Well, again, it's raining. And at what rate is it raining? Well, it's a constant rate, right? There's no change in the rate. So it is raining at a constant rate. So it's still raining, even though it's a flat line, but it's not raining harder or softer. It's raining at the same rate. So it's raining at a constant rate of what? 1 inch per hour. So that's what that flat line means. It's the rate. And so it's still raining. It's just not raining harder or raining softer. It's raining at exactly the same level between 3 a.m. and 4 a.m. What is the slope of the graph between B and C? So let's go rise over run. So first of all, it's negative. That's important to know. What's the rise and what's the run of that negative? So if I go up, it's 1 over. And then from 4 to 5, so B to C, 4 to 5 is also 1. So if you like, it goes down 1 and to the right 1. So altogether, the number would just be -1. Write a complete sentence again. So we need time to begin with. So 4 to 5 in this case is between 4 and 5 a.m. What is it doing? Well, the rainfall is doing something. And because we have a negative rate, what's happening? The rainfall is decreasing at a rate of 1 inch per hour per hour. You could also say it as 1 inch per hour squared. Both would be right. That's this concept of per. So you're already looking at a rate. What's the rate of a rate? Because that's what it really is. So the rate of a rate would be inches per hour squared or inches per hour per hour. I missed an important word here. What word did I miss here? Rate. So the rate of rainfall is decreasing at a rate of. So it's the rate of the rate. So in real words, it means it's raining softer, right? Going down. And it's consistently raining softer at a constant rate of decreasing. All right, integrate from 3 to 5. So what's one way to integrate is to find the area under the curve. So from 3 to 5, it's already shaded in. What shape do you see? A rectangle and a triangle, or a trapezoid? So anyways, I see a trapezoid. 1/2. The bases are 2 plus 1. That would be 3. And the height, which is 1. So if I put that together, that's 3 over 2. Or 1.5. Write a complete sentence. Explain what that means. What did you just find? So what's the time from 3 to 5? So from 3 a.m. to 5 a.m. it rained a total of 1.5 inches. So when we integrate, it's not a rate now. So others were rates, like question 15, inches per hour. Number 19, a rate of a rate, inches per hour per hour. When you integrate going the other way, the answer is just inches. It's a finite answer, not a rate. Approximate the value from 0 to 6 using geometric regions, and then show your computations. So if I look here, we already know the trapezoid area. That's 1.5. What is the approximate shape of the left part? Notice we had to use the word approximate because it's curvy. It's not an exact geometric shape. Do you see the triangle that could come from there? So here is a triangle on the left. How do you find the area of a triangle? It's half the base times the height. So it's 1/2, 3. So the triangle is 1/2 the base times the height. plus the trapezoid, which we already found. So 1/2 of 3 times 1 is actually 1.5 and 1.5. So altogether, the answer is 3. So again, I had to approximate it using a triangle and a trapezoid. Even though it wasn't exact, some is below, some's above, but it's a good shape that approximates what that is. Write a complete sentence. What did you just find? So that means, what's the time again? From what time from what time? From 12 a.m. to what? 6 a.m. Approximately. How many inches? 3 inches of what? Of rain. Fell. Done. The ability to write a simple sentence that includes the key facts. So if I have time and I have inches, I make sure that my sentence includes that, the axes, the horizontal axes, the vertical axes, and I answered the prompt and understand what it means. All right, please do your assignment. We will go over the homework first, and then you're going to have a quiz on this. All right, happy weekend.